Okay. Hello, everyone. We're in a wait period. We joined early and started recording early. Um, while we're waiting for other people to show up, there is some good discussion going on in the Kaggle chat. And I encourage everyone to look at that and participate.
By the way, Tom, before I go, I want to mention something that Sorav, our friend, he has COVID. He just sent me a message. He and his family that he cannot join today, and he's not that much, let's say, able to follow up with us. So we will wish him the best, he and everybody in the world, for this situation. Yes. Right now, I will apologize from everyone, and I will back soon in 10 minutes.
Okay. Gio, we get to catch up while we're being recorded on YouTube. I'm sure not many people will mind though. How are you?
I'm fine. Good. But I didn't understood
what
is happening.
So basically Guy's laptop's not working well. He had to start the recording early so he could go do dinner with his family because of Ramadan. And Sadef is going to continue the lecture a little bit, and then Guy's going to come on and explain some things. So he was just taking his leave there, but said he had to start the recording early. But I think Sadef and the other students will be here soon. And I was announcing that there's some really good discussion going on in the Kaggle chat. You don't have to be part of the Kaggle group to benefit from what we're discussing. So you might like that.
Yes, I want to, sorry, I want to go, but unfortunately these days I've been very busy, but I'm going to join as soon as possible. Hi, Jonathan.
No worries. Hi, Sadef.
Sadef, how are you?
Hello, everyone. Hi, Joanna. Hi, Tom. Hi, everyone.
Hey. Just so y'all know, we are already recording, but Geith needed to go do something. He'll be back as soon as possible. Jonathan, we had a good meeting today. We missed you dreadfully, but there's some good chat in Kaggle chat for you to look at.
Awesome.
Yeah. And Sadef, you might also enjoy the chat going on in Kaggle chat. What I was confessing to the group is I get used to my tools that I know and my methods that I know, and they work. But then it occurs to me, oh, maybe I should go look for some new methods. And that happens to me every once in a while. So just so everyone knows, Sorav has COVID, so he can't join us, but we should be praying for him and his family. And India, that's not good.
Yes.
By the way, regarding this chat in Kaggle, what is about and how you can get connected with that, and the link or.
Sadef, are you part of our Slack work group?
No.
Oh, that's a travesty. Direct message me on LinkedIn your email, and I will add you to it.
Okay.
Yeah, you need to be part of our family. I mean, completely part of our family.
Definitely, okay. But who? I mean, I don't have your email.
No, I mean on LinkedIn.
Okay.
Just send it to me that way.
Sure.
Yeah.
Sure.
That way we're not recording our emails out loud here on YouTube.
Yeah, sure. I understand.
Hi, Valerie, Avinash. Hi.
Nice to see you, Gio. How are you doing?
Fine. I'm very happy because Saturday is the family day.
Yes.
Yeah, I can see, you know, like how we spend time with family now. It's our family, but then, you know, outside family. Like,
yes, yes, because it's like waiting for this moment. It's so exciting. Hi, Sean.
I like your background, Giovanni. Giovanna.
Oh, thank you so much.
It's a Jupyter. It's like a soft skills,
yeah,
Python. Yeah, cool.
All the things that I love are here.
Yeah, I can see.
Thank you. Greg.
We'll just wait a couple of more minutes, Sadef.
Okay, that's perfectly fine with me.
Okay, good. So your last workshop went good, Gio?
Yes, it was
Looks
awesome.
like it did.
Yes, thank you for asking.
Yeah. Okay. Sadef, let's see if you can go on ahead
Share
and
my screen.
Yeah, let's make sure you can
sure.
do that. Oh, who can? Oh, we've got it all set up, so it's good.
It should
can start sharing.
work. Let's see. I mean, like it should, but then and you don't know really in reality what happened. So let's give it a try.
Oh. Hi, Dr. Sommer. Welcome. Excellent. There you go. Okay. Yeah, now's a good time to start, Sadef.
Okay. Hello, everyone. Happy Saturday, and I'm very happy to have this session to continuing the previous session on dealing with the class imbalance with you today. So I mean, for those who may not be participate last session, I just give a brief overview about the topic that we covered in the previous session. So as I mentioned in the previous session, class imbalance is one of the major problems that we have in a real world scenario. So assuming, especially in the medical use cases, that we are dealing sometimes with a rare disease, and in many cases that we have a lot of samples from a healthy patient and very few samples from a patient who has those specific pathology that we have in our database, and that's hurt the performance of learning algorithm that we want to design to be used with our clinician or our doctors who make a critical decision based on that. So by class imbalance, we have covered last time about the data set. So what I want to also mention that in this tutorial, unfortunately, we would not be able to run code of how we train the model, but I prepared kind of slides that I can show the result of experiment that I have conducted. But I will, after call, I will make this Jupyter notebook available for everyone. So who has the participant who has a GPU, or they have, like, they can let the code run even on the CPU and wait a little longer and they would be able to reproduce the results. Anyway, what we covered, for example, last time, we have been focused on one specific data set that we were dealing with the kind of malaria disease, that the image taken from a different cell, which is divided basically in a two type of a cell, infected cell and uninfected cell. And if we run, let me see if it works here. If we run the code, we will see that how it looks like. So basically, okay, yeah, it's run. So in overall, yeah, yeah, in reality, as I said, it does not really work. So I have to change the directory. So basically, what happened was that we have like a whole data set of 14,000 images, and we take 10,000 images for from uninfected image, like cell images, and only 300 image in overall from the infected one. In general, the data set itself, it is a balanced data set, but since we wanted to simulate the class imbalance, class imbalance, I had to like do this kind of data splitting. And what you could see, the distribution of a training sample would be something like that. So you can see that you have like around 10,000 images from one specific category, which we call the healthy patient, and very few portion of it. It's going to be, it is from infected cells. So the analogy for that would be real case scenario that you have a lot of healthy cases, but at the same time you have very few samples from patients who are having a rare kind of pathology. So previously, I mean, in the last meeting, I also said that in order to solve this problem, we are going toward the kind of method which we call it oversampling. By oversampling, it means that we artificially increase the number of our negative samples, such that we within each, so we would have the same number as we have in our infected, uninfected, or majority class in this case. So if we have, for example, 10 images from infected sample or minority class and 100 samples from majority class, what we do, we artificially repeat this process such that we have like 10 times more increase the number of infected or minority class, such that we will have at the end kind of 100 samples from infected or minority class and 100 samples from a majority class. It's basically artificially increasing the size of our minority class, such that somehow we would be able to remedy this problem. But if we do not do that, what would happen is basically it's happening to be a class imbalance. So I create a kind of code that I would like to share with you. So from last session, what we did, I show you that how we create. I'm not going to repeat all the process that we did last time, but to do kind of recap is that I provide you a kind of a code which you are able to have to artificially increase those samples and do the oversampling process. And now in this meeting, what I'm going to do is that to show you how now we are training the model. I had a discussion with the guys, and he said that he will speak maybe in next session, or and he cover the concept which we call that transfer learning, and also training and validation, how to do data splitting. But please bear with me, and then like accept whatever I said about like transfer learning, and he will cover in the next few sessions, and he will go to the more detail, so you would understand, you grasp the concept better maybe later on. But if you have any question, you can ask me. So what we do here is basically this is about this session. So what we do, we know that for training a neural network, we need to have a lot of data. But one common practice is that to get a pre-trained model, which is already trained on a huge amount of label samples. In this case, we call it ImageNet, which there are 1 million images in there, 1,000 which are split into 1,000 categories. And we already pre-trained our model. So we do not need to retrain our model from scratch, given, let's say, 1,000 or 10,000 samples that we have currently. So we use that like a model which already trained on that. And then we do, this step is nothing but the transfer learning. So we use that model, which we call in this case, we use ResNet 18. There are several variety. There are different variety of a pre-trained model exists, but in this case, I use ResNet 18. We have ResNet 34, we have ResNet 50, we have AlexNet, different variety of that, right? And what we did basically, since we are dealing with the two-class classification, I only modify the last fully connected unit. So I would not go to detail of that. I will, if any of you have a question, you can ask me later on, or Reis would, in the next meetings, he will cover, he will go to more detail about this specific topic. And then what we need to do is that we have like again, these are the standard approach that we are doing. We define an optimizer. We have like a cross entropy loss that basically, again, I would not go into detail, but it's important once you want to optimize your model, you use a kind of optimizer. And in this case, I use a cross entropy function because it's one of the common approach and a standard approach to go with. So regarding this part is very important.
Sadef,
important part of your code. Yes.
Just real quick. I want to make sure I'm tracking with you. Is ResNet a data set that you're going to train on, or is it a pre-trained model?
Our ResNet is a pre-trained model on ImageNet, which basically here in the code, what I did, you can see that it's written pre-trained true.
That's what I thought. Okay.
It's verified here. But if you put it pre-trained to false, then you can retrain your model from scratch.
Thank you.
You're very welcome. So this part is a very important part of the code that basically, as I tell, everything is ready. And if you have a computation power, or even you have like more time, you can let it to, you can easily let the code run, and overnight you will have the day after you will be able to reproduce my results. So, but what is important here is that you need to divide your data to training and validation set. We have in a standard setup, we have a training, validation, and test set. But here, I only divide it in two parts, train and validation, such that the training would be the sample that you pick it from your whole data set for teach your model what is positive class or infected and what is uninfected class. So, because at the very beginning, you need to teach your model that what you are looking for, right? And then validation set is we can consider it as a hold-up set, which is completely unseen during your training procedure, right? So what we do, once we divide our model to train and validation set, we let our model to be trained during the training procedure as easy as few lines of code, which you can find it here, right? And this part is a data loader, which we already defined it somewhere here. So if you go to a data loader part in a cell, you would be able to find that code, which I already did the process for you. So it's ready to go, basically. So you have like I created a data loader here for oversampling and without oversampling. If you want to consider oversampling, I define a kind of flag here for you, so you can put this one to true, so you use oversampling. Otherwise, you can set this to false, so you do not use oversampling. And you have a validation, which is unseen data for your model during training. So If you go, it is only a for loop. So it just train your model, and then here you do. I do not go to the, as I said, it would be out of the scope of this talk that I will discuss about the backpropagation and optimizer. And then once you're doing this process, once this process finish, you need to validate that how your model works properly. And if you do this process, I will go to result. That's what happens. So why oversampling is necessary? And why, if we have a class imbalance, as I wanted to show you here, we have like a lot of uninfected sample and very few infected samples. So what would happen if you repeat? Yes.
Sorry, there is a question from Tom, and there is also another question from Greg on the chat. So I think it's good to have it before the training, before showing the results.
Yeah, very good.
Tom, sorry for that. I will start with Greg's question.
Thank you.
How did you know to select ResNet 18 versus any other model?
Okay, perfect.
Is it by trial or error? What is exactly? I have something here, but I think your answer to it.
Yeah. So, there are several articles, and it was. I mean, as here in this call, our goal was not to introduce the best model possible, but it just basically showed that what the concept of oversampling is. I pick one off-the-shelf model, and I choose ResNet 18. You can choose whatever model that you feel like to use. So there is, I mean, like basically experimentally, they show that, for example, among ResNet 50, it works better compared to the other. It's like kind of a chicken and eggs problem. So if you want to use it, your model in a production setup, for example, in mobile device, it's better to use like a model which is like basically is not heavy weighted. While the accuracy, you might lose some accuracy, but at least you would be able to run it in a small device. In this case, ResNet 18, I choose it just because, I could use another approach. I mean, I just find that and I use that one. So there is no specific reason what's behind my choice here.
Okay, I just want to comment something because today we are only showing the result of oversampling. So we are not going in detail about the transfer learning. It will be our next session. According to that, when we are talking about the transfer learning and we understand exactly what is transfer learning, we will know sometimes why we choose this model, because it might be performed good on similar tasks. So it's something related to the trail. There is, as Sadak said, there is some articles telling you what is the best, but it's depending on your data situation, data nature. That means your understanding to the data and to the let's say experience that you have, or that whatever happened, best practices about this task, and also the trial part. You have to try and check what is the best. So Tom, please, your question.
Yeah, so Def, this is really good and interesting. Mine's kind of high level. Help me understand what you're doing with ResNet versus your own training. Is ResNet just a comparison mechanism? The pre-trained model is going to be compared to the one that you're training? Is that?
No, so if you, as ResNet is a big data, is a deep structure. If you need to, okay, you have two ways to train the model. So either you can use a without pre-train, I mean, no pre-trained model, which is all the weights they are initialized at the very beginning in a random setup, right? If they are random and the amount of sample that you have here is not enough to train the model from scratch, right? So the common practice that what we are doing is that we use a pre-trained model, which is trained on some big data set, and we apply the transfer learning. Here, as I did, it's a common practice. We apply the transfer learning for a smaller task, in this case, what is infected and what is uninfected. And we use the knowledge which the model learned from the big data set. I know that the task from ImageNet is not really relevant with our specific task, which is in a medical domain. But however, different articles shows that if you use the images which is trained already from a big task, from like natural image task in this case, and you apply the transfer learning and use it on the medical images, is performing better compared to a training model from scratch, which is...
You answered me perfectly. Let me see if I can restate it. It's basically, instead of randomizing our weights initially, and we're not really necessarily doing transfer learning, we just know that a pre-trained model that's not too far from what we're doing will do better than initial weight randomization.
Exactly.
Thank you. Thank you. Okay.
You helped me with my English. It's like, it was very hard to explain. Yeah. Thank you. Thank you, Tom. Exactly. So let's say now, what would be the impact of oversampling? Why we said that we need to do the oversampling? So if you run the code that I provided for you, you would get exactly the same result. You only need to change the flag of oversampling to true and false, and you would be able to reproduce exactly these two graphs. So the reason for that, now you can see that, if you are only focused on the no oversampling graph, you can see that, and then the blue indicating as the training accuracy, and then epochs is that number of the time that we are, I would not go to detail of that, but anyway, what you can see is that in the x-axis, we have epochs. It means that the number of each epoch means that the number of the time that you let that you let the model to see your whole training set. So it means that if you have like 10,000 images, your model run with a number of epochs is 4. It means that we go through across the whole 10,000 images 4 times. So in overall, our model see 40,000 samples. No, after each process, I should have eliminated 0.5 because it was an access problem. So if you consider here, you have I plot that across the four epochs, and you see that you get a very good accuracy on the training set, but then you see that you get a very bad accuracy on test set. Why this is happening? The reason behind that is that the number of, in a worst case scenario, 99% of our samples are coming from uninfected let's say class, right? And what happened here is that in a worst case scenario, if you become very good on predicting only our majority class, which is 99%, because our model has this capacity, has this opportunity to see our samples, the majority class, 9 times more than in the minority class. Even we are misclassify the minority class. In a worst case scenario, we would have a 99% accuracy. And then you see that the model is very good on predicting of a majority class, but it's very bad it's very bad to generalize toward a class which through the unseen samples. So it's very good on the seen samples during a training, but it becomes very bad if you are, for example, if you train your model from 40,000 samples, and then we give you 100 samples, infected and uninfected, from some other, sample set which your model did not see. Model is not able to predict that, so it's basically failed to generalize. So, but with the oversampling, what we can see, we are able to remedy this problem strongly. So you can see that after one epoch, with one epoch, you are able to get 95% accuracy exactly on the same set of the data with equally distributing between a minority class and majority class, your data set. And you can see that after one epoch, instead of getting like a 50% accuracy, you would be able to get like around 96% accuracy. Of course, you can see that if you continue training, the performance would drop. And there is a concept which we call that early stopping, which I would not go to the detail of that, because if you have like a class imbalance, you have to be very careful that you do not let the model to train a lot, because as I said, you artificially increasing your number of training sample, and the model after a few like epochs iteration, it would get intelligent enough to just see that, okay, those samples, they are artificially increasing. So in order to be also more clear here.
Sadaf, real quick before you go on.
Yes.
Are you saying past that knee on the previous slide, it's starting to become overtrained?
Exactly.
Okay.
So it's not, I mean, like it's not dropping like significantly, but if I'm quite sure if you continue training after like with 50 epochs, then you will continue to get lower and lower and lower, because I can see the trend that is going down and down. And yes, it's overtraining. So
okay.
In order to show you that, maybe I bring this one to the previous slide. Maybe here you can see that what I mean by this. So you can see that the model is like trained very good, and then here we call it confusion matrix. It basically, here it says that if the class is uninfected actually, and you predict it as the uninfected one, it means that 250, the total number of samples that I use for validation or test is 500. You see that you are able like to perfectly predict them like a uninfected class, because it's a majority class. Our model is able to predict them perfectly correctly, but also at the same time, it thinks that all our infected class are also uninfected. So this is the meaning of perfect meaning of oversampling. So all the time, it assigned the prediction to the majority class. So it's all the time it thinks that our prediction, whatever sample you give it to the model, it thinks that, okay, is infected because it's uninfected, because it has like a higher opportunity to see the uninfected class. While if I bring this one here after oversampling, the number of uninfected class which we are predicting as uninfected class is 200, the total number is 250, but 247 of them, they are uninfected, and actually we predict them as uninfected, while 3 of them, they are misclassified and we are not able to predict them, because 3 of uninfected class, they are actually uninfected, but we predict them as infected.
And just to belabor the obvious here, Sadaf, we would like this imbalance rather than the opposite. In other words, 3 that were actually infected. Wait, now am I looking at it backwards? I wonder. The label. Oh, shoot. This is not we would rather have this flipped, where we actually had the predicted was 21 false that were actually positive. Would have been better if that was the 3 and the other one was the 21, right?
Yeah, but then, yes, but however, we have no other choices, because basically once you are with the oversampling, I would say that you cannot really solve your problem, because you can solve your, I mean, if it's relative, no? If you look at this one and this one is a huge gain, right? So basically we were not able at all previously, without doing oversampling, predict anything. We have been always predicting wrongly. But however, here, as we are having like, they are like infected, as we are having a lot of sample from an infected class, basically our chance to get them all right is very low, no? And I would say that the data set here, in this case, it was very simple. In more complicated data set, in many cases, I was not able to get like a significant improvement, no? So, because it's just difficult. The more data you have, the better it is. But if you have such a class imbalance, this is the only, this is one of the most effective approach you can stick on. And of course, as I mentioned, you would not be able to solve this problem 100%. So that's a chicken and eggs problem anyway. So you will have that.
Yeah, absolutely. It's just a bummer. There's more false negatives because you'd wish that there were fewer false negatives than false positives. But that's all I was pointing out. It's the best we can do.
Yes, Tom, I want to add something. Yes, I agree with Tom, but this is right now we are talking about the kind of business we are running. Here we are talking about the medical field, and in the medical field, both false positive is more appreciated, because even if it's false positive, there is a chance to, let's say, to solve this problem. But if it's false negative,
exactly.
Yes, especially consider it not from malaria, go to the COVID case, for example. But also, it's not depending on this. We can say, by my example next week, I will show how sometimes you are able to play this game. But again, it's depending on the data that you have, the original data that you have. Sometimes you may play some games to raise the false positive instead of raising the false negative. But again, it's depending on the data that you have and the case that you are studying. But technically, what SADC shows, it's perfect the case that what is the benefit of oversampling and where it's used and how it's used. Yes, SADC.
Exactly. So as guys he mentioned, if we are having more false positive, that's not. It's at the worst case scenario. Doctor, he said that this patient has for example, this disease or malaria, and then he do a test, and then it turns out okay, he doesn't have. But if the person has the malaria and then said that he doesn't have a malaria, and then he doesn't do the follow-up checkup, then he would risk his life, and that's a major problem that we are dealing with in a healthcare domain actually. So, however, regarding this specific case, it was it wasn't. I was not really optimizing the model that to get the best performance, but then basically to give the message, okay, how oversampling works compared to the without doing oversampling. But yeah, I agree with you, and the guys that that we wish to have maybe more false positive rather than false negative. Yeah. Okay, so this is the end of my a presentation, and I would encourage you to basically, if you are interested on the topic, to please, what you need to do basically to run the code is you need to install PyTorch and MonAI, which is as simple as one conda command. If you go to the PyTorch website, you will see depend on your operating system, you would be able to install it easily. And MonAI, pip install MonAI, you just finished everything. And then what you need to do, basically, you need to change this directory. This is my personal directory, and you need to download the data, which we would put also the link of that. I would put the link in the notebook. And the last thing that you need to do, maybe this is very, very important, is that if you want to run it with the oversampling, please flag this one to true. And if you do not want to use it, just put it as false. And then, yeah, you would be able to reproduce everything perfectly.
So Daph, real quick, can you either to your presentation or to your notebook add your favorite N, you choose the number, imbalance data set methods of dealing with imbalanced data sets. I know there's different ones, but it would be nice with someone with your background to express which ones you like best and why. It may be that your answer is, oh, I don't like any of them better than the other. I have to test which one works better. I don't know. But if you could add a little, one slide that says that briefly, because that covers Avanish's question too, I think.
Okay. Mm-hmm. Yeah, they are in overall what we have. Basically, there are 3 different methods. I would add them. One of them, this is my favorite that I presented to you. It's easy to reproduce the results. And basically, this is the first method to go when I encounter with the class imbalance. So that was this is my favorite one. The other approach that we are using is especially in deep learning is a penalization. So what you do basically is nothing but very simple. You add kind of parameter here that I would put the kind of explanation how you can do that. No, so this is kind of weight which I computed already for class for oversampling, and you need to change it a little bit here.
Because 20 years ago,
yeah, because when I think about it, this is all about dealing with the class imbalance. And
exactly.
So knowing different methods, Avinash, I'm really glad you asked this question. I think knowing the different methods is key. And I would also encourage one other thing, and Sadef, I don't mind if you disagree with me as I say this. As you guys understand the principles by which class imbalance is dealt with, I think it's okay for you to explore creating your own method. In fact, I'm thinking of one right now that I would like to try, which deals with, okay, I identify the records that deal with the class that is imbalanced, and I find some statistical methods using the features to reproduce with variance based on the distribution I'm seeing in each of the features to produce additional labels for the class that's imbalanced. But that would be saying, okay, now that I understand the principles, I'll come up with my own approach. And maybe that approach already exists, but I know Smote from talking to people, working out challenges online with them. Smote's very popular, SMOTE. I don't know, Sadef, if you've used that one.
Well, it's I was using. I mean, like I've heard of it. We are artificially increasing like a number of samples, but basically, I have not seen anyone in a deep learning using SMOTE. I mean, to the best of my knowledge. So maybe someone used that. No, maybe at a kind of pre-processing stage, they get their data and then they apply this SMOTE, and then they generate like artificially like more training samples. I have not seen, but I know that there are like in sklearn, there are a bunch of these approaches that you can easily play with that and create your artificially increase your training samples to the majority class, right? So one approach that I also like it, sometimes this class imbalance is not so severe. So for example, what you do here is that, for example, let's say if the portion between the class balance and imbalance is like around 50%, right? What I do, I work also on undersampling, which turns out the results would not be really bad. No, so for me, it works in some use cases. The approach like SMOTE, I honestly say I haven't seen anyone that use in a deep learning, but then I see that many people in random one they use the random forest or working with the tabular data. Mainly they are using like SMOTE or other well-established oversampling approaches.
I just want to, Sadaf, to continue on your point. I think you already mentioned something related to the weighted loss function. That means you are calculating, finding the loss function for each class, and according to that, instead of oversampling, you are going to assign a weight for the loss function. According to that, you will maximize or increase the effect of the minority class contribution and the total loss. This is how you do it. I think the second method, which
exactly.
is exactly. I think this is also a very effective way sometimes. And if you, I would like to speak about it next week. Instead of oversampling, we are increasing the contribution of the minor class with the overall loss function. This is used a lot with the oversampling, one of them in deep learning scenarios.
Exactly, and then like the thing is that the reason that I didn't discuss here about like a penalization, I call this method penalization, is that you need to first define what is the weight, and basically give a good example of like a logistic regression that one video from Andreng exists that I really like it. It was one of his first video tutorial when he launched Coursera, machine learning. It was not a specialization, machine learning course actually. He explained very nicely this oversampling concept with the logistic regression. So the thing is that if you guys want to explain about, I know you have your own strategy how to explain that, but then I think the logistic regression need to be explained, and at the same time that what does it mean by weight here? So it's complicated. For me, oversampling.
Yes, we have to reach that point. Yes, we have to reach that point. Exactly. Avinash, I think you have something. Avinash, please.
Am I audible?
Yes, we can hear you.
Yeah. So all those approaches, like I tried some of them in the classical machine learning problems, but I'm not sure like how we can utilize those approaches for the deep learning problems wherein the images are there. So I still have confusion regarding that. Like if if we have a data set wherein it contains all those images, so how we can balance all those things? See, one approach was you make it balanced by reducing the number of the data points, and you select the number of data points from the majority classes wherein which should be equal to your minority classes. That is one approach. But like other approaches are you give some weights to the minority classes and generate the images. Like but I'm still having confusion, like how can we do that with the images?
So the thing is that I did not reduce my majority class to the minority class. This sample this concept that you're discussing is the undersampling approach. The concept and undersampling was not possible for me in this specific scenario, because as you can see, the number of a majority class is 10,000, the number of a minority class is 300. So if I want to reduce my 10,000 sample to 300 sample, then I would lose a lot of information. So this is not, I would say, that recommended in this kind of scenario that you can see, that you see here. Undersampling makes sense that you have, like, I don't know, like you have a majority class to 10,000 and minority class, let's say, to 5,000 or 6,000. So you can do undersampling. For dealing with this kind of scenario that I'm showing right now, if the concept is simple, the concept is simple such that you need to increase the number of if you were, I don't know if you have been in my last presentation or no. It's very misfortunate that I cannot really run that. So what happened is that the number of samples, so we need to apply the oversampling using a kind of function that I defined it in the previous lecture, such that we artificially increase our number of like a sample within a batch. Let's say it's difficult to say. So let's say you have 10,000 samples, or let's say 100 samples from a majority class and 10 images from minority class, right? So you have 10 times more majority class. If you split your data, which we call it batch one, no? Split your data, and then let's say within this specific batch of data, what we need to do is that we artificially, assuming that generate the image that repeat. Yeah, let's say we copy this minority class and we oversample that, such that we will have 100 positive class, majority class, and 100 negative class. I know it looks a little bit odd that it works somehow for deep learning, but it is working. No, so the conclusion is that if you're copying the existing data and increasing your number of samples to the majority class, which in this case is 10 times more, and you would have exactly the same number, almost the same number of like a majority class and minority class, the learning algorithm is able to understand that. Again, I repeat that it looks a little bit odd that it works, but it works. So just copying an increasing number of your samples. It's not really complicated. You don't need to really do anything. It's just copying. You know what I mean?
Avinash,
Yeah.
I want to say something here. We have two things in the deep learning scenario. We have to consider two things. First, sensitivity about the class itself. How our network, our neural, or our model is, how much is sensitive about this class or this label, let's say. So when we have the data balanced on both sides, even if it's repeated, so we are raising the sensitivity about this class. This is the first consideration. The second consideration is covering the full patterns that we have to cover. Now, this one oversampling is not helping. That's why it's better to look for more data. It's better to find more data, but sometimes it's not possible to do that. So these two considerations, we have to keep it in mind. First of all, it's sensitivity about the class. That means, let's say our neural networks or our model is dealing fairly with both classes, or more than both two classes even. It's dealing fairly with all the classes that we have. That means it's trained for the same number of data to be sensitive on. Now, the second consideration is this data, it's covering all the expected patterns from this. Now, this is, I can speak about it later by next week. Since I will speak about the transfer learning, I will take some time to speak about this one. How this oversampling, it's helping and it's giving the results, but that means it's not the 100% solution for all the problems. This is what we have to understand.
Real quick, Sadaf, I think I understood you. You're saying that rather than get fancy with how you balance, you can just make copies of the imbalance set and do it over and over. And it works pretty well. That's so cool, because you can spend a lot of energy on how you grow that imbalance, or the smaller set of the two or more. And it's really comforting to know that, no, it works pretty well just to copy it.
Yeah, because look, once you are doing the copy, it's not exactly the copy. Look at this data transform that we are doing, right? Once you are doing this copy, we are doing resize. Well, of course, we do resizing for all of them, but we apply random flip, we apply random rotate, we apply random Gaussian noise. although we are copying 10 times, but randomly, we are also applying another transformation on top of it, right? So we add somehow diversity in the data. Although, as also Reis mentioned, it's good always to have more data. But then if you're, as I said, on the other hand, if you're dealing with a rare disease, where even the doctor having a problem, fortunately, to get more data about that because fortunately not many people have this disease. How we do not have this data. So this is the only, one of the approach that we can rely on that, and it shows that it works better compared to the case that we do not apply any transformation or any copying on top of that. And as you said, just copy, let this transformation on top of that to happen, and look at the results. So in some cases it works, in some cases does not, but this is what we need to see during practice. Any question?
I just really enjoyed some takeaways. The copying was kind of cool, and the understanding this transform part, but also that was quite insightful, that you could just use a pre-trained model that's not exactly related to what we're doing. It's not really transfer learning. It's just a better initialization method, correct?
It is better initialization if you put it in that way. So look, I'm working to give you kind of information that how good they are, and it's really strange that they're working. Now I'm working, for example, on the voice recognitions, right? So it's really amazing that once you're using this pre-trained model on the ImageNet, which has nothing to do actually with the spectrum frequency domain. They're in nature, they're completely different. But then once you use this pre-trained model, even though they are trained on ImageNet, and you use this, you initialize it from this model, which is pre-trained on ImageNet, you see that, you look at the performance and say, wow, how it could be possible, because they are two different, completely different stuff, but they're working. It works. So yeah, to answer your question, exactly. So it's again, you are transferring the weight, so you're copying the weight. So some people, they said that it's transfer learning. Some people, they said it's copying the weight. But in nature, we are doing the same thing.
No, but Sadat, I want to highlight something. It's possible to follow the both scenarios, but in general, when you are transfer learning, we are on the training phase, we are training the fully connected layers only. That means we will consider ourselves happy with with the weights on the conv layer, and then we are training only the fully connected layer, which is at the end, it's customized according to our scenario. So sometimes we are doing this, and I think in your scenario you are doing this also. I wasn't
in this scenario. I let the model to train to back propagate through whole net.
The whole. Okay.
Yeah. So for me, the transfer learning is both. So you can use, as you said, we don't go to detail. So
okay. Keep it for the next week.
Yeah, I think it was. For me, it was an interesting a discussion, but I think for audience, it's just overwhelming with a lot of new topics. So
okay, Jonathan, I think you have a question before we have to stop. So your question quickly.
Yeah. So the bit that we just seen in order, the transformation, you're applying each of those transformations randomly to a random image before you pass it into the pre-trained data set, correct?
Into the pre-trained model, yes.
Yeah. Okay. Cool.
Yeah, it's first of all, this is forget about this, because it's kind of, we need to do it all the time because of a specific transformation, because the the size of an image is 220, like 256 by 256 by 3. But then since the this package, it requires that our image be 3 by 200 by 256 by 256. It just said that ensure that challenge like a channel first. So this is one transformation. This apply for all images that we have here. For all images, we apply resize, which we want that all our images being resized, being in the same